In this video we're going to look at mass and weight. Just pause the video here if you want to read through the bit of information about mass and weight if you've not covered this yet. And here's the formula we're going to be using. It's weight measured in newtons equals mass measured in kilograms multiplied by gravitational field strength measured in newtons per kilogram. Sometimes gravitational field strength can be also measured in meters per second squared, but usually it's more convenient to write it or to express it in newtons per kilogram. The symbols for weight, the symbol for weight is W, the symbol for mass is lowercase m, and the symbol for gravitational field strength is lowercase g. Some questions will tell you to use G equals 10 newtons per kilogram if it doesn't need very high precision, but usually most GCSE and A-level questions now will require you to use G equals 9.81 newtons per kilogram, which is what we're going to use in the following examples. So for converting mass to weight, all you have to do is multiply the mass by this number here, 9.81. So if we do 15 multiplied by 9.81, we get 147 newtons. To go the other way, you have to divide through the weight by this number, 9.81, to arrive at 99.9 kilograms. So here we multiply, going from mass to weight, we multiply by this number, and here we're going from weight to mass, so we divide by the number. Just some short descriptions here, whether and we need to decide whether it's a mass or a weight. So a force is a weight. If it's measured in kilograms, it's going to be mass. If it's measured in newtons, it's going to be weight. If it decreases, if you go to the moon, that's weight. A measure of how difficult it is to accelerate a body, that's mass. That's why the gravitational field strength is sometimes called the acceleration due to gravity, and it's measured in meters per second squared. So how difficult it is to accelerate that body, that really is a description of inertia, and so it's the change in the motion of a body, and so this is mass, and it's coming from the F equals ma equation, which you may have covered already. So force equals mass times acceleration. So for a given mass, how much force is required to accelerate it, that's where it's coming from. It's nothing to do with the weight of the object. Caused by the gravitational attraction of another body, that's weight. So anything with mass, if it's within a gravitational field of another body, then it's going to have weight as well. So anything with mass has a gravitational field itself, and so those gravitational fields will interact with each other, and they will produce a force which is known as weight. Calculate the following weights. 1. A man of mass 75.0 kg on the surface of the Earth. So to find the weight, we take the mass and we multiply it by g. 75 multiplied by 9.81 gives 736 newtons. 2. A man of mass 75.0 kg, so the same mass as in question 1, on the surface of the moon. So now instead of the Earth, it's on the moon, and so the value of g is lower. But the process is exactly the same. We multiply the mass times the value of g that we're using here now for the moon. That's g little m, subscript m here, representing the moon. Mass is still the same, 75. G is now smaller, 1.6 instead of 9.81, and that gives 120 newtons. So just to note that the value of G on the moon is roughly 1/6 of that on the Earth. Question 3. A man on the surface of the Earth who has a weight of 114 newtons on the moon. So on the moon, how much mass? We can find how much mass the person has first of all. So this is an example of a question which requires two main steps really. You can't directly calculate the weight of the person on the Earth, right? You've got to first of all know how much mass you're dealing with. So to do that, we'd look at the weight which we're given, 814, and we convert that to a mass using the relevant value of G. It's talking about on the moon. We know what the weight of it is on the moon, so we need to use this value of 1.6 for G. We couldn't use 9.81 because we're not talking about the Earth at this point. So we do 814 divided by 1.6 gives us 508.75 kg. Don't round up at this point. Put all those decimal places in. Don't go ridiculous though. If there's more decimal places, just put a couple in for now. And then we calculate on Earth, what is the weight? What would the weight be of this mass? So this mass now is not changing. We've managed to calculate the mass of the person, and it's not going to change when it goes to the Earth. So he goes to the Earth and his mass stays the same, but now the gravity's gone up to 9.81. So that means that we can calculate what his weight is on the Earth. Now we're not really interested in this little one down here, so we put it to 3 significant figures, and that's because in the question here, 75.0, that's 3 significant figures. So we're working to the same number of significant figures as in the question. So that's 3 significant figures, so our final answer also goes to 3 significant figures.